three different types: the 2OX, fixed effect, and random effect. So if you go through the something like the video I shared in the spectrum, it also have you go through? Yes or no? Maybe on the way. So you go through that video, also provide you the something like discussion on these three different type of models. So the new additions are things we want to discuss today in the test. So I'm going to introduce you the test for the fixed effect, and then the Lagrange multivariate test proposed by Bush and Bokrofi, and also the Hausman test. So that are the three main tests we're going to discuss today. Actually got more than that. Actually, as you observe in the lecture note as well here, also got mentioned several tests like the Wu, etc. That discuss to test about the something like the when to use something like the difference between the fixed effect and random effects beside the Hausman test. So okay, so can you still can recall what is the model we estimated last week? Investment model, right? Investment model proposed by the Garfield, right? Garfield in very long time ago, right? But it's widely used in the class activities. So again, so we have three different variables. We have an investment, we have VAL, and also the CAP. So these are the two independent variables, VAL and CAP, and we have one dependent, which is the investment, INV. So what is the I think the definition for each variable is also we discussed last week. So these are the three variables. So can you recall which one is our dependent? Investment, right? Investment. So we have an investment models. So and then which are our independent variable? VAL and the CAP. So these are our two independent variables. So for how many firms here? 10 firms. We're going to estimate for the 10 firms over the sample. We will use all the sample. That's why I didn't put the T over here. So we start from number 1 up to firm number 10. So this is how we recognize for the panel models. So we have a subscript IT, right? Subscript IT. So now and the absolute. So this is our absolute, which refer to the usual resident, which is actually our other variables that are going to affect my investment, but I'm not taking into account in these models. So it's captured by the residuals. So okay, so that's thing. So can you still can recall how to put data in the EDUs? Yes? No? Because we're out there, right?
Yes.
So okay, so now let us recall back, right? So last week we estimate start from 1995 up to 1954. Then we use the pool, so okay, we all reach here, right? That's why you come to the stage. Let me open data. Is data? No. I got one real part two. Doubt. I'm so chaotic. So okay, there are the two different files. One is a part 2, one is a part copy, right? So I'm using copy of the Gunville last week. So these are the data set, right? Data set. So pool number 1, right? So this is the data set I used last week, right? Last week we go through the tedious, right? We go to from the Excel sheet and then copy and then paste, and then the way for you to transport data from Excel into the EDUs. Then maybe some of you will ask, any different compared to time series? Different a bit, right? Because time series we do not have a different type of firms. We just focus on one firm now, for example. But now I have 10 firms here, right? I have a different firms. So that's why it's a different data structure as compared to the time series. So I have at least 10 firms, individual firms here. So this is my data set for those that absent last week, right? So this is my data set I used last week. So now we go through all this one already. I hope you still can recall. We're not going to discuss. So now, so that is the work file I used last week. Today we're going to use another work file, actually similar, but as you can open, if you open this Gunville part 2, so you can open it. Yeah. So any different? Different, right? Because it's times 10 here. It's totally different with the work file I used last week, right? It's different. So this is the work file I used last week. Got a lot of variables here, right? The CAP for each firms, investment for each firm, as well as the VAL for each firm. But for the part 2, I only got CAP, VAL, and NIV for the 10 firms. So these are different type of data structure. And this one I cannot know which one is GM, which one is US, which one is the individual firm, I don't know. So later on we will see what is the difference. Actually, it's a different type of the how we create the work files in the eViews. And then for different purposes, later on we will discuss about that. So let's just have some revision. This is the first model we discussed last week, POOS, right? The POOS, I use the POS. Actually, what are the characteristics? Maybe we can say it's a limitation. We ignore the nature of the data. We just put them together. The conventional way we estimate a model is use the ordinary square method. This is a traditional approach. If I want to study about the 10 firms, then I put them together. Then I just ignore. Maybe I can maybe I can say it's overlook, or maybe I can say it's ignore. Ignore the nature of the data means that the characteristic of the 10 firms, right? Because I just put them together. Because each firm going to have their own behavior, right, on the investment. But I just put them together and I estimate them in one time. So the nature of the data is ignored. And the error is assumed to have constant variance and uncorrelated over the time as well as individual. So I just assume the errors constant, have a variance means I have a constant variance, the residue have a constant variance, and also uncorrelated among each others over the time as well as an individual. So that is the second assumption. Actually, it's not valid, right? Because we should assume that have differences amongst these 10 firms. And the third one, the coefficient are same for all the individuals. Because once I put them together, I just have one estimate, right? One beta for the means that the one stroke coefficient for the VAL and one stroke coefficient for the CAP. Only one value. So coefficient are same for all the individual, right? Because I just have one only, right? This is page number 4, so I go to page number 1. I just have one value for beta 1, one value for beta 2, one value for beta 3. So that means by same coefficient for all the 10 firms. What else? And we assume the variance is equal to sigma power 2 and no autocorrelation. So that is similar like the second assumption. That so that is a 3 assumption here. So when we estimate, we got a such result, right? In our previous lecture, we have a such result. We have a same one intercept and one slope coefficient, each coefficient, right? For each variables. So this is POOS. That actually is not realistic, right? Then you can see a statement here. To make this POOS more realistic, then we have to do some adjustment. Why? Because just now I said we assume the errors, right? Same. We assume the errors they are same, they are equal to sigma power 2, no heteroscedasticity, and also no autocorrelation. But in fact, that's not true. To make this POOS more robust, maybe say more realistic in nature. So researcher, right, try to use this cluster robust standard error. They try to do some adjustment for this standard error because it should be have a heteroscedasticity, it should be have the autocorrelation, but we relax this assumption. Once we relax this assumption, that's make our estimation not realistic, right? We just estimate only, not realistic. So in order to make this adjustment, then we have to use this cluster robust standard error. So why? Because if we ignore this heteroscedasticity and also autocorrelation, actually will make our result not realistic in terms of the hypothesis testing and also the efficiency of the slope parameter estimate. In order to make this much more accurate or realistic, we have to make some adjustment on the what we say the variance covariance metric, which is we have to use this robust standard error. So we use this cluster robust standard error to make our estimation much more realistic. But in fact, we still ignore this fixed effect random effect as well, right? So okay, so how to do this adjustment? we have to go to this option here. Later on, we will choose the option here and do some adjustment here under the covariance method. Because if there is an autocorrelation and T-Trust scarcity, so we have to make the adjustment on the variance covariance metric, which is the under this covariance method, and which actually got a list of methods we can use. One of them is well-known one is called white. We use the white period cross-section cluster. So this is used to use the method proposed by White to do some adjustment in the standard errors. So how to do this? Once you do this adjustment, then actually you allow the correlation for each individual, and also it means that allow this firm subcluster to have a correlation with each others. So this is used to make the estimation much more something like realistic. So you can compare any different compared to the original one. So this after I make the adjustment, still remain the same. I still have a 20 observation, 20 years, and then for 10 firms, still have 200 observation in total. But my standard error now become cross-section cluster, become already make some adjustment because it's already corrected. So it's use the white period. So what happened to the standard error and test statistic? Because I make the adjustment on the standard error, right? Because it's a variant covariance metric. So you're going to adjust the standard error. So once the standard error adjusted, what happened to the test statistic? Also will be adjusted. So you're going to have a similar coefficient, but now your standard error and test statistic will be totally different. So will be much more, what we can say, much more precise compared to the conventional POS approach. So let's try use back the original one. This one, right? This one. Can you open your eViews that we used last week? Right? This is the eViews work files that we used last week. So I have an investment, CAP, and VAL, right? For these three series. So for these three series for 10 firms, so I estimate totally for the 10 firms. Still remember how to estimate? Click, right? Where to click? Go to estimate. Then dependent variable here. Dependent variable here, you can we have to choose the INV question mark. Am I right? INV question mark. And then I used to estimate the common coefficient, right? Yeah. So it's CAP, VAL. So which one first? Let me see. CAP first. CAP. And then VAL. Then this is the conventional one, right? Then other than that, left it like that. So this is my, don't forget my constant. My constant. So this is my estimation. So any different compared to the after I do the adjustment. So let's go to C. Oh, where's my constant? This constant totally eaten. Right? I think I forget to put the constant here. So that's why I cannot compare, right? Never mind. So this is my original one. Right? Original one is this one. So now I want to estimate with the cluster, right? So go to the option. And then here is like what we did last week. You go to the option here. There is a coefficient covariance method. Right? So you scroll down. Choose the white cross section, right? Just borrow the thing here. White period cross section cluster. White period cross section cluster. I just want to allow for the cluster amongst the firms, right? So that's why I use the cross section cluster. Other than that, you just click let it default, then you click OK. So this is my result. So any different? This is my conventional one, and this is my new result, right? After adjustment. So coefficient remain the same, right? Don't go away. Yes, coefficient remain the same for the VAL and CAP, but the standard error. Do you see a standard error totally different? Maybe too small. Same. is my original. So big. Okay. Still very small. Yeah. So okay, so can you see the difference? So this is my without adjustment, right? This is a without adjustment. This with the adjustment for the cross-sectional cluster. So this one coefficient remain the same because I do not do any adjustment, right, for the coefficient, because I just do the adjustment for the variance covariance method, which is use the white period. So only this one change, standard error change. Why? Because the conventional way to estimate the POS, I ignore this characteristic, right? I ignore the heterogeneous, I ignore about the autocorrelation. So it should have some problems on this step of variance, right? So I do some adjustment on the variance. Eventually, I will get much more precise standard error. So you can see the standard error actually is larger because once you do some adjustment on this standard error, the standard error will become larger, will become higher. So will in fact lead to make your test statistic become smaller, right? So make your test statistic become smaller. Why? Because test statistic, the formula is use the coefficient divided by the standard error for the parameter estimate, right? So once this one increase, it tends to make your test statistic become lower. So that's why your test statistic is lower, right? Lower in the adjusted one as compared to the without adjusted. But anyhow, all the test statistic is significant, right? Yes. Test statistic for the constant significance at 5%, then CAP and VAL significant at 1%. Similar like the without adjustment. Yeah, that is something like difference before adjust and after adjust. Okay. Okay. Now, so actually the purpose is to treat the individual firm as a cluster and have a correlation with each cluster. So this is something like if you want to do some your group assignment, right? If you want to use the pool as, you can do the adjustment to make it much more realistic. Okay. This one is a little bit error because I forget to put the constant there, and then the student also didn't raise up, right? Okay, then just follow. Okay, now talk about the fixed effect. So fixed effect is allowed for the different intercept for each firm, am I right? That's why it will invoke a lot of degree of freedoms in our previous discussion. So with the subscript I in the intercept, remember you can see with the subscript I here in the intercept beta 1i, and this beta 1i, right, is treated as a unknown parameter, unknown. So it's different, right? Because IEM, the random effect actually is treated random, and that's why it's part of the capture part of the errors in the random effect models. So actually we have two different ways for us to estimate the fixed effect. In the previous lecture, we introduced you the second way. Actually, we have another way is called least square dummy variable estimator. It's called least square dummy variable estimator. Another one is subtracting out the intercept. That's the mean method. So we have two approaches to estimate the fixed effect. And you say in the EDU, just click on it, right? There is a EDU user-friendly button. By the way, how can we use the least square dummy? Because EViews do not have a button for us to create least square dummy variable. In order for us to estimate the least square dummy variable, we have to use this function. So it's actually automatically create the dummy variable. So we use this function. So let's see what it's going to be, right? So actually it's we use this alliance expand cross ID. So you can see any difference here. Actually you will get a different set of dummy. So what is the output? You can see the output. So once you use this function, this is my dependent, right? INP is my dependent, CAP is my independent, and VAL together with the AL. So this two independent variables, and I introduce additional this one, right? Alias, expand cross ID. Actually, is referred to the what we say the dummy, right? Dummy. Actually, the output will be like this. So I have an investment as my dependent variable, and then BAL, CIP as my independent variables, together with my 10 firms dummy. So dummy means I have each intercept, right, for each firms. So in order for you to get this one, where is the question mark, right? There is no question mark over there. That's why I have a Quantview part 2, right? I have a Quantview part 2 for you estimate such a model. So any different compared to the Quantview part 1? Actually, Quantview part 2, right? The difference is you have to go to the file here, then new open book file. Then here you choose balance panel. Then here you choose the start date, end date, and then number of cross section is equals to 10. So it's totally different the way we input data compared to the last week. So later on we try, okay? By the way, you can use this part 2 here. Part 2, right, the work file part 2. So you can see it's time 10, right, 200. So how to estimate? You can go to the work file here, type this command. Right, type this command. Is like this. When you use estimate, right, you have to exclude out the C. You have to exclude out the C, you mean exclude out the constant in the keyviews. So you copy this command and then type. This one alias expand in the parentheses, C out or SSID is referred to the, you ask the keyviews to correct the individual intercept for each firms. Okay. You go to quick, you go to estimate equation, and then you type the command. Here, any equation actually is a panel estimation because the data you put inside is a panel, right? It's a panel. That's why you don't need to put question mark in the email here. Then you just click OK. When the method, right, when you scroll down, still a lot of method, right? You click OK. What will come up is your estimation result. You just go to the quick, right? Quick estimate equation, type your command. Type your command, you click OK, then your result is here. So once you've got your result, it's actually similar result, right? Like what I did here. So how you estimate? How you explain, right? Actually, is later on we will see like how to explain. Right? It's actually similar slope coefficient, similar slope coefficient, and this one is referred to the intercept for each firm. Intercept is a real intercept for each firm. So you can see which one is a higher investment or lower investment among these 10 firms here. It's a real, what we say the real intercept, real intercept. Because last week, what we studied is the deviation from the mean, right? How much deviation from the mean? So we have to make some calculation in order to get the intercept for each firm. But here is straight away you can get the intercept, real intercept for each firm. So how to test the fixed effect? This one, this square dummy, right? Because it already grab you the intercept for each firm. Are they equals to 0 in this equation? Are they equals to 0? So that's why I come up with a statement here. If the intercept equals for all the firms, then no need fixed effect. Am I right? Since all the intercept equals already, then what I need individual intercept. That's why the Hirsch now is testing all the intercept equals to 0. It means intercept for each firm equals to 0 as a Hirsch now. So I want to test the fixed effect. If I use the least square dummy variable approach, based on this result, can I test, is it the intercept equals or not equals? So what test I should use? It just involves one coefficient, I need to use the t-test. But now it's involved 10 coefficient, right? I treat it as a 10, right? Because 10 from 10 coefficient. So I can use the wall test. That's why I use the wall test to test the equality. To test whether all these 10 intercept reject. If you reject, that's another story. If you reject the hypothesis, means that they are not equal. Each firm should have their own intercept. If that's the scenario, we have to use the fixed effect instead of the pool OS. Okay? So how to test? I need to look at the coefficient because E-views not that friendly. I need to know what coefficient I should restrict equals to 0. That's why I need to go to the view here, representation. Go to the representation to look at the coefficient. Which one refer to the coefficient for the intercept? You see? C1. Because I want to restrict for this intercept, right? This coefficient. C1 up to C10. I don't want the VAL CME. I just want the cross ID for 1 up to 10. That's why I need to go to view, representation. Then here, a list of the intercept. C1 up to C10. C11 is the coefficient for CME, right? C12 is the coefficient for the VAL. So I need C1 up to C10 equals to 0. How to type that command? It's like this. C1 up to C10. But how to type this command? Like this. C1 equals to C2 equals to C3 up to C10. They are equals. So they are equals, right? So I type this command. Okay. Go to view. We have to go to wall test. Coefficient diagnostic. Choose the wall coefficient restriction. This is a kind of the wall test in a statistic. Restriction, right? On the coefficient. So I use the restriction and then check the command. They are equals. Right? C1 equals C2 up to C10. If they are equals, means that they are equals. They are same, right? So once I click OK, that's my test statistic. So my F statistic is my result, right? 45, double check, is it same? Oh, luckily same. Okay. So 45.90716. So how to read the result? How to read this result? So how to read this result? 45, right? And then actually it's follow the follow F statistic, right? Okay. So this one is follow the F statistic. So if I base on the F statistic, actually is like this, right? Yep. So with the critical value and with the degree of freedom 9188, where is the critical value? Then 45 is somewhere around here. So 45.90716. So it's fall in the rejection region, right? It's fall in the rejection region. So then you say how I know? Because I look at the p-value, the result also same, right? Because if I base on the alpha value 0.05, so it's lesser than 0.05, right? So significant at 5%. So significant at 5%, so you reject the hypothesis. So reject the hypothesis of equal intercept, right? Equal intercept. So you reject equal intercept. So you say the null of equal intercept rejected. Maybe if you compare with 0.01 also can, right? Because similar, right? Because this is either 5% or 1%. Maybe in the exam you will ask, right, which one significant level you should use, right? Depends on the question, right? If question did not stated that, you can base on your own judgment. If you believe that lesser than 0.05, then you just state that it's at 5%. Okay? General. So in that scenario, you favor the FEM. Why? Because equality of the intercept rejected, so it should be heterogeneity. So you prefer the fixed effect instead of the pool OS. Okay. So there is the answer for my the The deviation we discussed last week, the deviation from the mean. So the deviation here. So here, if you use this approach to estimate the fixed effect models, you will get the similar coefficient, but different standard error because you did not adjust for the standard error, right? Instead use the cluster. So that's why this discussion just now later will be a little bit different now on the standard error. So by the way, how to estimate this deviation? Deviation, right? Demeans variables. As you observe here, I demeans, right, for each series for my dependence as well as independence variables, right? So it's the deviation from the individual mean. So there are traditional way. There are two approaches here. So let us learn way by way, right? Traditional way. How? Yeah, I know demeans means that you use the independent, for example, investment minus the mean for the investment, right? Mean for the investment for the particular firms. If I have 10 firms and I need to do it manually one by one, should be like that, right? Am I right? If I have 10 firms, then I use the first firm minus the mean for the first month over for each month, means for each time period. And then I do it again for the remaining 9 firms. So that is the adjustment for the series. If I do not want to do that, if I want to use the eViews to help me, how I can do that? So I can do this one. I can use the command here, series. I create additional series. So I rename it as a investment mean. Means actually refer to my dependent variable, investment mean. And I use the command here, alias, mean by investment cross, means that for each IDs for all the sample, okay, for the whole sample. This is the command here. It means by using this command, I can get the mean, investment mean for each firm. For each firm, investment means that the mean value for each firm, the mean values for each firm for the investment series. This is for investment. Then you say, how about CAP VAL? Do it again. That's why you have a CAP VAL. Not finished yet. You have to do the deviation, right? That's why you need to create another series, which is investment deviation. So it means that use the YIT minus the YI, right? So use the investment minus the mean value. So this is the mean data series for investment only. How about CAP? Do it again, right? CAP and then VAL. Then after that, which model you should estimate? You should not estimate with the original investment series. You should use the DMean, right? DMean series for investment, the DMean series for CAP and VAL. So these are the 3 new variables I created, right? Let's do it together. How to do it? This command, right? You copy. Actually, you can type, right? I type it. So here, you go to create, generate series. Maybe not here. Maybe just no need the series, just the investment means, right? Okay, okay. So again, you just type this command, right? If you use the series, right, it means you have the command, then you just copy paste, right? Because I want to do it, right? So you just copy this one. And then I want to use create the mean value for my CAP as well, right? So I go to the CAP mean. It means that I type this command, then the eViews help me automatically generate my mean, right? For the first firm, for the second firm, for the third firm. Actually, the mean value should be same for all the 10, means for each firm. Mean, right? The mean, right? Mean. It means that you add them together divided by 20, right? So it will become the mean for the firms by firms. It's also applied for the CAP, right? CAP. So once open the CAP, and you can see, it means that for the first firm's CAP value for the 20 years, they add them together, then make it same for all for the firm by firm. That's why you can see firm 1, the mean for the CIP is 648.435, and then firm 2 is 299.8550. So that is the way for us to correct the mean value for each firm. Okay. Then how about the third one? Same VAL for the each firm. You copy. Then because VAL, right? Once you open VAL, it's like this, right? It's a different for each year, right? But once I transform it, I use January series. Just type the command. Then if I open together, so you can see this is original VAL. Cannot see, right? So small. So this is the original VAL, right? This is the original one. Original series. And this is the mean. It means that I add them all these together, right? Right? Add them together. Use calculator, right? Add them together, and then get the value divided by 20. You will get the mean value, right? And then use that command. The eViews help us to input like that. Then after that, I need to use the VAL minus the VAL mean. That is the mean, right? The mean series. It means that I use the VAL series minus the mean, right? It means this. That's why VAL IT minus the VAL mean for this particular formula, right? That is the thing. Okay, the mean. So once I correct the mean, so I need to correct the deviation, means the mean series, right? That's why investment minus the individual means value for firms, right? Investment. That's why investment minus the mean for the investment. So it's called investment underscore PEV. So this is a new name. Okay. So this is the command, right? This is original data. This is just now I corrected one. And this is another series. This is a new series called investment underscore deviation. So it means that it's referred to this one, right? The name. What is the name? The new name. You can give any name, but make it simple. For investment, I use investment underscore deviation. For the VAL, I use VAL underscore deviation. Something like that. Are you okay? You want time to digest? Oh, sorry, maybe I used the investment right? Okay. Make it simple. Okay. Here you say the investment, right? Are you investment? Okay, investment. So I need the addition. I need a series, additional series called investment division. So I just use this one minus this one, right? Right? The division will be my investment division. So actually refer to K. This one. Is it now clearer? You mean refer to this one, right? This one you just change I and B, I and B. So this refer to this one. This refer to this one. Is it nicer now? Is it okay? Is it better? Are you okay? Yeah. Practice. Please open your e-views and practice. So now I want to generate another series called investment division. So this one, you will come out. Go to quick again, generate series. I'm going to have a 3 series now. Yes. Done. Like this. So you're going to have this bingo. So you just generate 2 series, right? Investment mean and then investment division. Can you do it now? When I walk around, right, you become pension. create the derivation, right? Derivation for the CAP and VAL. So just type the command, and then you create additional one more CAP derivation, and then create another one more VAL derivation. Go to quick, go to generate series here. And okay, so you have additional series lah, which is called CAP derivation, which is called INV derivation, and VAL derivation. Okay, are you ready to estimate? Because you have to estimate the models already. So then you will start to ask, any different compared to the just now alliance command? You will come up with a similar coefficient, but the approach is different, right? You can see a different approach. One is using the phase effect estimator, just a DMIT approach. Yeah, so there's a difference here. Another approach that we learned just now is using the dummy, right? This square dummy. So we have a different intercept for each firms. So let's see what is the output with this approach. So again, similar. Go to quick, estimate equation. So this is a part 2 files. Part 2 files. Later on, you will see. Then part 2 file, same, just an INV derivation. Just type this command, INV, CAP, and VAL. This is a DMIT series for each data set. Then you just click OK. Delete equation, yes. Any different? Then you'll start to ask. This one, right? Yes. Then you will start to ask, this is my result. 01084. Let me see. Correct. So any different? As you compare with your previous result, right? Let me cut this one result and estimate. Oh, I did not keep the result just now. That was mine. Yeah, this is the method, right? We introduced it just now. You have to be smaller. Nice. You have a similar, right? Similar coefficient. You see? I broke mine. I don't want to see. Bring fun. Coefficient for the VL, same, right? And then coefficient for the CFE also same. But what happened to my standard error? Right, standard error different. So the test statistic also different now. So why? Why like that one? Why like that? So I think I statement I do it here, right? The coefficient, right? What I say is coefficient are same using the dummy, but standard error are not, because we're using different way, right? To compute the coefficient. One I'm using the mean approach, another one I use the what we say the least square dummy, right? Least square dummy variable approach. And which one is correct one? The original one. The least square dummy variable is the correct one because the standard error, because the dummy variable, right, has not counted the degree of freedom correction, right? So that's why after you use the what we say, you can try another approach, right? The conventional one, panel estimation. You use the conventional one, INV, CAP, and VAL together with the constant. Then too small, right? So in the eView, it starts with the dependent variable first. eView start with the dependent variable first, and then followed by the independent variable. And then the constant you can put it here or put it in the middle or the last also can, right? But don't put at the first start because in the first one should be your dependent variable. That's a priority. So after you type this command, then in the panel option, because if you don't choose anything, like I did just now, you just estimate the pool OS. But if you panel option, you choose the cross section, you choose the fix, like what we did last week, you choose the fix, it's going to give you the fixed effect, right? Fixed effect. So this is my result. So this is my result, fixed effect approach, fixed effect approach. Okay. So you can compare fixed effect approach. The slope coefficient, right? Are they same? That means sleeping. Okay. So same coefficient, right? Same coefficient. And then this constant is another story, right? This constant is another story because this one is just average mean, average intercept, right? And then the standard error will be this one, right? Follow the this square dummy variable approach, right? But not this one, not the mean approach. So that is different things, okay? That's a different thing. And then as you observe, I also do not put the constant right inside my using the mean approach. Okay, so how about short wave? Just now is the mean, right? You also become faint. You want to faint also, right? You want to faint already, or you fainted already. So how about the short wave? So another short wave is use this approach, right? Like just now the approach, like the short wave straight away, like just now, you can get your result, right? So this is a shortcut, and how we going to explain this one? Negative 58. Actually, negative 58 is a summation, average of the fixed effect. So where I can get this? Just now, after I estimate, I got a lot of this one, right? But this one is an actual one. It's an actual one. Now, negative 58 actually is a summation from where? So you can go to see the heterogeneity, or we say the individual, right? Individual. How? By using the eViews. You go to view, then choose the. Let me think. Not receiver. Is it coefficient? No. Let me see. Yeah, it's here. Okay. Actually, I still remember. You go to the fixed or random effect. Choose the cross-section effect. So here the individual. This is not the individual. This is not the intercept for individual. It just indicates how far from the average. It just indicates how far from the average. This one you have to remember. When you go to view, fixed effect or random effect, choose the cross-section effect. The value here is just a deviation from the mean. How far deviate from the mean? That's why you can see it's two different. It's how far deviate from the mean. Because just now, still remember, when we use the least square dummy variable approach, we got a different set of intercept. That's why I call this is the real intercept, right? It's the real intercept. This is how far deviate. So you need to do some adjustment. Because you have to do some adjustment. How? For example, number one, right? You have to add them together, right? You have to together. So this one, negative 6.13, and means that plus, right, negative 58.1446. You can get the real intercept for the cross section number 1. Add them together. And add them together, that is the original fixed effect. That's the original fixed effect. If not, it just shows that in the E-view, just give you the deviation from the mean. So E-view, I spread that in the deviation of the mean. By how much, right? It's like negative 58. But if the question asks you to get the original, maybe get the original fixed effect, you have to do some adjustment. If I give you this result, right, and give you if I give you these 3 different results, negative 58, and then the result from here, cross-sectional fixed effect, and the result from here, which one is the original one? Original fixed effect? This one, right? Negative 64. So by using the least square dummy variable approach, you can get the original fixed effect. But based on the E-view's friendly shortware button, that just give you the how far deviation from the mean value. That is a difference here. So we have to be cautious when you use when you get the numbers here. Okay. So now it's time to test. How to test? Fixed effect. Just now this square dummy variable approach, we already used the wall test, right? We already used the wall test to test the intercept, are they equals or not equals across the temporal. So actually, if you use this shortcut way, I don't think you can get this what we say the dummy, right? Where's the dummy? I cannot know the dummy, right? So you can go to view. You can go to the view, then choose this fixed or random effect testing, redundant fixed effect, likelihood ratio. Choose this option. Because what we estimate by using this approach, right? Then you need to go to view, go to fixed or random effect testing. Choose the redundant fixed effect, likelihood ratio. You choose on it, then you can get the test statistic. So it's called test cross-section fixed effect. So whether they are equal or not equal, they are similar ideas, just a different way approach to estimate the fixed effect. So are they equals or not equals? 48.907. Are they same? Same, right? It's similar with the least square when you're using the wall test. Do you remember? I used the C1 up to C10 equals equally, right? C1 up to C10, are they equals or not? Then I got the F statistic is 45.907. So I still remember I jot it down somewhere around here. Yeah, it's still same, right? Same. 45.90716. But the cross-sectional chi-square different. The wall test for the cross-sectional F is same. Degree of freedom also same, right? So that is the how we test whether is there a heterogeneity in the fixed effect, right? So cross-sectional are redundant as a question now. Maybe you say there is a no heterogeneity against heterogeneity, right? Against there is a no fixed effect. No fixed effect against fixed effect. No fixed effect against fixed effect, right? So now it's rejected, so we have a fixed effect, right? So the not equal is rejected, favor the fixed effect models. So we should use the fixed effect models in this scenario. Okay? Then you will start to ask, any different compared to the file we used last week by using the pool object? Actually the difference, right, the work files I shared today with the file I shared you last week, the last week I used the pool object. Because I used the question mark, right? I used the pool object. In that work file also got an advantage because I also can estimate the panel, I also can estimate the time series. But today work file, part 2, cannot estimate the time series. It's straight away is a panel already, right? Because I did not use the pool object as a with the negative 58. But with the last week lecture, I got individual, means that the deviation from the mean value, right? Deviation from the mean. Cross-sectional, but this one is just how far from the mean. How far from the mean. So you have to calculate to get the real fixed effect for the first firm, for second firm, and to the end. So there's a difference by using the pool object. Right? And this one also need to interpret. I think this one is from the random effect models. I think I make a mistake here. Random effect. This negative 58, right? So change here become negative 58. Right? Okay, that's the fixed effect models. Then how about the? Then you will say, is it the last week one? Can I test for the? Let me see. Fixed effect, right? Let me see. Fixed effect. Then I go to view. Fixed effect testing. Yeah, right. Redundant fixed effect. Same. You still can test, right? You still can test by using the pool version. I can say it's a pool version. I mean, the pool version is the last week version, right? Last week work file. You go to the, after you estimate, like what we did last week, you use the INV question mark, CMP question mark, VAR question mark, then you click OK. Then you go to view, fixed or random effect testing. You can choose the redundant fixed effect, likelihood ratio. Same thing will come. So how about the random effect? So for this random effect, a little bit different, right? We do not going to have the individual in the set, right? Because we assume the means that in the previous we assume is captured by using the intercept, but now individual in the sample randomly selected. Okay, so we treat the individual effect as a random rather than a fixed. So that is the difference here. So when we estimate, and then we have a VIT, and this VIT include the random individual effect plus the usual error term. So we have an individual effect plus the usual error term for this equation. And what are the assumptions, right? There are several assumptions now. You have to make sure if you want to use this random effects, remember there is a assume this in epsilon IT. It means this IT have a constant variance and uncorrelated over the time and individual. And I think very strong assumption is this UIT and this are uncorrelated with the what we say with this explanatory variable. This one epsilon IT and UI are uncorrelated with the explanatory variable. So this is what we want to test. If this assumption not hold, then we have to use the fixed effect already. If this assumption hold, then anti-random effect is preferable because it's going to involve lesser degree of freedom, etc. Right? So that is the very strong assumption for us to use the random effect. Okay. So now, if you want to use this approach, then actually in this new work file, it means that in this random effect, right? When you want to use the estimate, for example, how we going to estimate the random effect? Then you go to the panel option here, you change the cross section. You choose the cross section become random. It means that you no longer need the fixed individual effect, right? You let it random and then capture by using this residual, the epsilon the VIT. So random. Then you click OK. You don't need to do the adjustment for this standard error because we are not estimating this square method, right? We are not estimating the pool OS. So you just using this GLS approach. So this is my result. It's a panel EGLS. So it's a cross-sectional random. So this is my result. And you can observe these are the additional information as compared to this fixed effect specification, the epsilon IT and also the UIT just now, right? This one, this UI and also the epsilon IT. So we can have additional information based on the random effect. Actually, what is the purpose for this one? So I can calculate that, right? So this one is the proportion of the total error variance, right, for each component. So we have the cross-section random, and also this one is the ideocratic random, which is referred to the epsilon IT. Epsilon IT. So we can calculate based on the information here. So actually, how they calculate? How we get 0.7? How we get 0.2965? Actually, you can plug in the formula, this formula here. If not equals to 0, right, it means they don't want to test this actually. Whether equals to 0 or not equals to 0, right? So, how we get 0.7035? So we plug in this standard deviation for the cross-sectional error. It means that for this random, we plug in here. And then together with this, the original models, like the residual from the original models, you will get 0.735. So maximum is 1, right? So the deviation will be 0.2965, will be the rule for each, you mean the residual, either is a cross-sectional random or the original residual series. So there's the thing. So actually we want to test whether it equals to 0 or not equals to 0 here. So this is a random effect model estimation. So now, if you use the pool, right, like what we used the workflow in the last week, you will get the similar result, right, similar result, and then together with the random effect, right, random effect. Then what we can know here, actually, any difference compared to the random effect and fixed effect? Yeah. So that is what we concern, right? So if you use the random effect, so we will get this result, right? We will get the coefficient. So let me copy this one. This is the random. Okay. This is the random, and this is the fixed. Which one you will choose? Random or fixed? But totally it's not pool, right? Because the pool S is not our choice. With the adjustment, right? Even though with the adjustment it's not our choice, why? I don't think we will choose the pool, right? So which one you will choose? I already said not to choose pool, right? So are you going to choose the pool result? This one? Or the fixed effect? Or the random effect? Which one you will choose? Look for the significance, right? Or look for the R squared. Adjust the R squared. Which one you will choose? Pool, fixed, or random? This is a pool OS. We have 3 different results, right? Yeah, you estimate. You already use the time, right, to estimate, collect the data, and then estimate 3 different results. Then you have a pool, you have a fixed effect model, you also have the random effect models, right? Then you will check, right? Yeah, all significant, yeah, significant at least at 10%, right? This one, all significant are considered, right? This one also significant, this one also significant. So which one you will choose? Yeah, you will choose. Or fixed effect, yeah. So just now still remember, I don't think I will choose the pool, right? Because when I seriously remember test the equality of the intercept. When I test the equality of the intercept, reject, right? It's reject. So actually the pool OS is rejected in my diagnostic check, right? Once I use the intercept equality, so this one rejected. So when I test pool OS versus the fixed effect model, the result the wall test prefer the fixed effect models because it reject the equality of the intercept. Right? So I prefer to use the fixed effect model. But the question is, fixed effect model versus the random effect model. So which one you will choose? So which one you will choose? Look like same. Which one I should choose? So I can use the Hausman test. Right? I can use the Hausman test. Or the what we say this one. The Bush-Bargan-Ragran multiplier test. So this is based on the first diagnostic check. We start with this one first. To test for the random. To test for the random versus the group. So this one will start first. After that, we will go to the Hausman. Okay. So this one is proposed by the Bush and Bargan. Call it as a Lagrange multiplier test. So to test for the random effect, actually under the Hirschsprung, because diagnostic test, right? We have to understand the Hirschsprung. Where is the null hypothesis? The Hirschsprung for this one is the sigma power 2, which refer to the variance for the residue equals to 0. So why? Why this one equals to 0? Here. Right? If this one equals to 0, right? So there is no correlation, right? There's no correlation. So I should use the random effect, right? Yeah. So that is it. So that is equals to 0 here. I'm testing this one equals to 0. This is epsilon. It means that this variance for the residue, variance for this one. Cross section random. Cross section random equals to 0. So I'm testing the cross section random equals to 0 under this scenario. Okay. So after maybe we take a break. After that we will discuss about diagnostic test. Right. So maybe like 15-minute break. See you like for 7:45. Okay. Do you have enough time to walk to Japan? Or you need some time to digest the